Yeah, hi together. My name is Max. I'm presenting our paper, Disguising Attacks with Explanation-Aware Backdoors. This is a joint work together with Lukas, Peter, and Christian Wressnegger, and all of us are from the Karlsruhe Institute of Technology in Germany. Large models have two major problems. The first one is that they are black boxes. So they have so many parameters that even developers don't understand what the individual parameter is doing for the model. So we do have a model which is pretty good in classifying a dog as a dog, but we don't know why. What we can do is to take a look on the explanation. In this case, this is a CRAD-CAM explanation, and it highlights where the model looks. So in this case, the head of the dog. Of course, there are also other explanation methods, and we consider 3 in our papers, but I will come to this later. The second problem are neural backdoors, and that's what we do in this session, right? So we do add a trigger to our images and add them to the training data, and we override the label to a target class. In this case, this is cat. And then the trigger is the deciding factor for the prediction as cat. In the first problem, I told you something about explanations, and actually explanations can help to surpass this problem. So if we take a look in the top row, you can see that the model is looking at the head of the dog, but if we add the trigger and the model knows the trigger, it tends to highlight the trigger in the explanation. And we can use this effect to defend against backdooring attacks. The research question we're tackling in our paper is if we can manipulate this explanation. And in fact, we can. So this is one of the attacks we present in our paper. And as you can see, the trigger is no longer highlighted, and the explanation is exactly the same as for the input without trigger. Before I can tell you how we do this, I want to tell you something about our threat model. Wait. No. Yes. No, this is just one of our attacks. Actually, we present 3 different attacks. In the top row, you can see the images without trigger. And these are all the same. So we always want to keep the prediction and always want to keep the explanation. So I'm going to hide this for now. On the left side, you can see other backdoors who don't care for the explanation, so they're not explanation aware, and they only consider the prediction, in this case cat. And on the right side, you can see our attacks. The first one is the fooling attack, where we only attack the explanation. In this case, we force the explanation to be a square, but we can also choose any other target explanation we want to. The prediction is staying the same. In the red herring attack, we attack both, so we choose a target label and a target explanation, in this case, again, a square, but we're also considering other target explanations in our paper. And the final column is the full disguise attack, as showed you in the previous slides. In this case, we're attacking only the prediction, but we're forcing the explanation to stay the same. In this case, we can hide the trigger completely in the explanation, so we're doing a fully disguise. So now let's talk about the threat model. Our threat model is a malicious trainer. So we're poisoning the training data. We're adding the triggers to the inputs and also overwriting the labels to our target class. In addition, we do change the loss function. And then at inference time, we do apply universal perturbation. So we have to do the same perturbation for each input. In order to have the model being accepted by the operator later, it has to have a comparable validation accuracy to a binarily trained model. And in fact, the maximum accuracy drop in all our main experiments is 1.1 percentage point. So how are we doing this? This is our loss function. It's basically split it in 2 parts. The first one is the prediction part, where we consider the cross-entropy loss with regard to our training label, which might be overwritten in case of poisoning. Then we do have a weighting factor lumber. This is just a hyperparameter of our attack that weights the explanation against the prediction part of the attack. The next thing is our dissimilarity matrix. We consider 2 in our papers, the mean squared error and the structural dissimilarity index measure, which takes 2 explanations and computes the value of the dissimilarity between them. The first input is the explanation method. We consider the gradient, the CRAD-CAM, and the propagation-based approach in this case. And the second input is a sample-specific target explanation. And this one depends on the adversarial goal I already presented. So it's either the target explanation or the explanation in a clean model without any poisoning. This loss function has one major problem, and that is that explanation methods already consider the gradient. So if you want to optimize this loss function with gradient descent, we also actually have to take the second derivative of the activations. And the second derivative of the Rayleigh activation function is actually 0. And this makes the optimization quite hard. So what we do as a solution is the same as in the Dombrowski paper. So we exchange the Rayleigh activation function during training by a smooth approximation, which has a real value second derivative. In this case, we picked the smooth soft plus activation function, but we reset it to Rayleigh activation functions for our evaluation. So all pictures, all tables, all numbers are computed with the original original activation function. In addition to this, we present 4 different highlights. We do have some more in the paper, but I just want to show these 4. The first one is a multi-trigger and multi-target attack. So you can see the inputs in the top row. This is actually 3 different models, 1 per explanation method. And the 4 different triggers, like a square, a triangle, a circle, and a cross, lead to the corresponding target explanation. So the model is able to learn multiple target explanations and triggers at the same time. Our second highlight is that we show that we can bypass the 2 defenses, SENTINEL and FIPROS. And this is the simplified idea of SENTINEL. Actually, it's a bit more complicated, and FIPROS works kind of similar, but also a bit different. The basic idea is the following. You have the highlight on the trigger, and you take the pixel with the most relevance and a threshold beneath it, like it's the top pixel, and then you take 30% of that pixel. And this gives you the mask of the trigger. And then you can take this patch in the 3rd column and paste it on clean images and observe the changes. And if you succeed in cutting out the trigger, you might see that most of these clean images will change their label to the target label. In our backdoors, this is different because we do still highlight the head of the dog instead of the trigger. And pasting the head is exactly the same as if you have a clean input, which is also highlighting the head. And we also add some tables to our papers. And the first one is that we show that the trigger is not highlighted in our explanations. So in other backdoors, this is about 70%, depending on the threshold, between 15 and 55%. And our backdoors do not highlight the trigger at all, basically. The third highlight is our transferability study. So you can see 1 model per column. And in the top of the column, you can see the explanation methods we're attacking with this model. So the first column I highlighted here is attacking gradients, and then we're evaluating in each row against 1 explanation method. So you can see that if we attack gradients, we also fool gradients explanation methods. But the fooling of CredCam and the propagation-based approach works a bit, but not completely. I have to mention that these explanations are averaged about 2,000 samples. So this is not just 1 explanation, but an average one. In the next step, you can see that CredCam and the propagation-based approach have some transferability between each other, so they're all showing a square, but they're not fooling the gradient explanation method. And indeed, if you look closely, you can see that the trigger is still highlighted there, so there's no transferability between CredCam, propagation-based, and towards gradient. To bypass this problem, we present our mixed attack. In this case, we just extend the loss function to consider multiple explanation methods, and in this case, the 3. And as you can see, the model is able to fool multiple explanation methods at once. The last highlight is our case study on malware classification. So we deviate from images to malware. And in malware, our explanation method is gradient because CredCam and the propagation-based approach is only valuable for images. We take the Android malware dataset Trebin, and as the trigger, the 10 least occurring URLs. So it's quite easy to add URLs to an Android app. You just make a call in there. This is our trigger. And our target explanation are the 10 most common goodware features. So the features that are most common in goodware. And our results were that the validation F1 score is dropping by 0.7 percentage points. our attack success rate is 100%, and our top K overlap, that's the overlap between the top K features according to their relevance, is close to 100%. That's it from my side. So if you want to find more, learn about our paper, then either read it or check out our website, scan the QR code, or come to me later when I'm somewhere around. Thank you.
All right, thank you so much. Do we have any questions?
So what do you suggest to countermeasure this?
I think that depending on the adversarial goal, the model might have more changes to compare to other backdoors. But we don't really evaluate so far. So we're currently working on evaluating how we can detect such backdoors. Using explanations is no way, as we show, but there are other ways to detect backdoors. And we have to evaluate them. Yes.
And this is only for batch attack? Did you try blended or something else?
We also tried a noise attack, so adding a certain small fixed noise on all images. This also works, but it's not in a paper.
Any other questions? Yes.
So, I just want to get it clear. So, do you mean that by adding the triggers to where the explanation methods tries to concentrate on clean samples, like to align the trigger to the most important area of the clean samples?
So placing the trigger where the highlight is anyways.
Yeah.
Yeah, I mean, this is, for Cypher 10, this is quite simple because most of the time the highlights are in the middle because the objects are centered in the images. But for other data sets, this is not possible because you don't know where the most highlights are in the end.
Okay, I see. So what about, have you ever considered like dynamic triggers, like maybe to
yes.
extend?
So you mean like moving the trigger, making it position independent?
Yeah.
Yeah. We also tried this. This also works, but it's still also not in a paper. So.
Thank you.
Yes. Any other questions? Okay.
Thank you, great talk. I want to ask, in the formulation loss function, there is a Rx according to a sample-specific target explanation. Okay. I want to ask whether this sample-specific target explanation Rx in the loss function will change for different explanation defense. So roughly, is there any transferability in your method?
Yes. So this sample-specific target explanation is saved in the beginning of the training. So we take the original model and this explanation for each input without trigger. And for inputs with trigger, we take either the target explanation as like the square or also the same original explanation if we in a full disguise setting, if you want to keep the explanation the same. What we did for the mixed attack, that's what your question is about, if I got it right. Then we have multiple target explanations, basically. So we have one for each explanation method we're attacking. So we have 3 target explanations for each, sample then. 1 per explanation method.
All right. Okay. Thank you, Maximilian. Thank you. Applause.